Alright, Brainiacs, buckle up because it's about to get funky. I'm Hugo, buzzed and ready. Let's pounce on today's mind blower. I'm on the hunt for knowledge, and dude, this one is perfectly perplexing. Here's a riddle. What magical table fits in your backpack, holds every kind of stuff in the universe, and tells you how that stuff behaves, like tiny superheroes? Boom, the periodic table. Let's roar and explore. No guts, no glory. This chart is like a treasure map for atoms, showing patterns that repeat like my favorite drum beat. Oh, what is it? It's a big grid of boxes called elements. Each box is one kind of atom. The secret code in every box is the atomic number. How many tiny protons sit in the atom's middle? That number decides who the element is. For real. The boxes go in rows called periods and columns called groups. Slide across a row and the outer electron spots fill up. Drop down a column and you meet a family with similar habits, like a pack of lions who all love the same snack. Elements in a group act alike because their outer electrons match. This repeating pattern has a fancy name, the periodic law. When you list elements by atomic number, their properties come back in a pattern. That is why group 1, the alkali metals, all love to lose one electron and go kaboom with water. And over in group 17, the halogens like to grab one electron and make salty teams. Now check out the blocks, S, P, D, and F. Those letters tell you which kind of little parking space the outer electrons are using. S block on the left, P block on the right, D block in the middle for the shiny transition metals, and the F block is that stretchy row that sometimes gets moved under the table to save space. Why do these blocks matter? Because electrons sit in shells and subshells, and the way they fill up explains trends, like who is big or small, who holds electrons tight, and who shares them easily. It is like musical chairs for electrons, and the band is quantum beats, baby. Quick history sprint. Back in 1869, Dmitri Mendeleev lined up elements by their properties and even left empty seats for ones not found yet. He predicted how those missing elements would act. Later, scientists proved the true order is by atomic number, not mass, which locked the pattern in place and made the table a rocket booster for science. The periodic table is a giant puzzle of the universe. Each piece is tiny, but when you click them together, you get fireworks, fluffy clouds, salty oceans, shiny phones, and, tasty honey. Okay, switching rivers, surprising fact alert. Bismuth was long treated like a stable, chill dude, but scientists found it very slowly gives off a tiny alpha puff. Its half-life is an unimaginably huge time, far longer than the age of the universe. Talk about the slowest sloth ever. Now pause for a moment. Some parts of the table spark friendly debates. Take hydrogen. Should it sit with the alkali metals in group 1 because it has one outer electron, or should it hang with the halogens because it can act like a -1 hydride and it is a diatomic gas? Different clues point in different directions. Helium is another spicy peanut. It has 2 electrons in an S shell, so it is S blocked by electrons, but it's super inert and matches the noble gases best. That is why you usually see helium sitting proudly in group 18 with the cool do not react crew. Group 3 has its own puzzle too. Modern evidence says the best fit is scandium, yttrium, lutetium, and lawrencium together. That keeps the F block as a neat 14-wide series and matches how those elements behave, tidy like a well-swept burrow. Big picture again. Periodicity happens because electron patterns repeat when new shells start. Close a shell with a noble gas, start a new row, and boom, familiar families show up again. That is why you can predict a new element's style by peeking at its neighbors. And now hold on to your fur. This next bit is bonkers. Back to hydrogen for a showdown. Sometimes it is like an alkali avenger dropping an electron and teaming up as H+. Other times it is a halogen hero grabbing an electron and becoming H-. Which squad does it join? Here is the twist. The answer depends on the story it's in. In acids, it acts more like group 1 vibes. In some compounds, it leans halogeny. Most charts park it in group 1 for simplicity, but scientists keep an open mind. It's like choosing teams in jungle soccer. Sometimes you play striker, sometimes goalie, still the same superstar. Next up is a doozy. Get ready to meet elements that go boom in style. We will peek at the colors of fireworks and the stardust blasts that build new atoms. Oh, that was a wild ride. Give yourself a tail wagging high five. Keep your curiosity ignited and your minds fueled with knowledge. Stay curious, little ones, and that's the tail end of that tale for real.